So we've been looking at this procedure for testing hypotheses about a population median. In this lecture video, what we're going to look at is its applicability to skewed and heavy-tailed distributions. If you think back to your previous courses, nearly all of the inference procedures that you learned in the prerequisite statistics course are based on an assumption that the population being sampled is normally distributed for the response variable being measured and analyzed. One of the reasons for this is because the mathematics can be pushed through in developing the methodology for the procedures. Now, one of the things that I have told nearly all of my classes over the nearly 30 years that I've been teaching statistics at the college level is the following. Assumptions made in developing a statistical methodology become limitations on the situations to which that methodology can be applied. Now, this means that while the standard procedures are applicable and will perform as expected in terms of type 1 and type 2 error rates, power, coverage probabilities, etc., when the assumptions upon which they're based are satisfied, they are not necessarily applicable in situations where those assumptions are not met, and hence may not and probably won't perform as expected in those situations. This translates into type 1 error rates that are too high, power being too low, confidence interval coverage probabilities being too low, and so forth. In fact, their performance in such situations may be quite far from what is expected. The bottom line is that we need to be careful and perhaps somewhat hesitant in applying the standard procedures in situations where the assumptions upon which they're based are known to be violated. Now, while the standard procedures do have some robustness with respect to some types of assumptions being violated, they may be less robust with respect to violations of other types of assumptions. So as an example, some of the standard procedures are somewhat robust with respect to skewness in the population being sampled, but are less robust when the population being sampled has greater kurtosis than the normal distribution. Now, many of the explanations and examples that we've used up to this point in the presentation of this procedure for testing hypotheses about a population median have used symmetric distributions, and in particular normal distributions. This has been done mainly for convenience and because of our familiarity in working with this distribution from our prerequisite statistics course. So if you think back to some of the examples I've shown, and the explanations of the development of the methodology itself, I used some bell-shaped curves, and in some cases actually said, let's suppose that the data come from a normal distribution. But I did that primarily because that's what we're used to dealing with, and in terms of talking about probabilities and areas under curves, those would be very familiar to us. So that's why I have utilized those symmetric and in some cases normal distributions. However, neither normality nor even symmetry of the population being sampled is necessary for the procedure that we've presented to be applicable. This procedure for testing hypotheses about a population median is applicable for any continuous distribution. The population of values can be highly skewed or even have high kurtosis. The procedure remains valid even in these types of situations. Now, to emphasize this, what I'm going to do is go back and run through the development again, and in this run through we're going to not use any kind of pictures of normal distributions. We'll use some other kinds of distributions, and we're also going to pay careful attention to any assumptions that we make. So our review of the development of this procedure. Alright, so this is where we pretty much started in our development of this procedure back in the initial lecture video for this procedure. We defined a population median, and we talked about the population median in the context of a continuous distribution. So if y is a continuous random variable, then the conditions that were stated to define a population median can be stated in the following way. So we've got these two conditions that are met if this value cap m is a population median for a continuous distribution. The first condition is that the probability that the random variable y is less than or equal to cap m is equal to 0.5. And also, the probability that the random variable y is greater than cap m is also equal to 0.5. And so these were the results upon which much of what we were doing was based. And notice that the only assumption we make here is that the random variable y is a continuous random variable. So now we're going to quickly revisit the development of a right-tailed hypothesis test about a population median, and we're going to be careful to note any assumptions that we make. All right, so let's let y1, y2, and so forth up to y sub n be a random sample from a continuous population with median cap m. Now, in the context of this right-tailed test, our goal is to develop such a test where the null hypothesis says that the population median is less than or equal to this specified value, this hypothesized value, cap m sub 0, and the alternative is that the population median is greater than the hypothesized value, cap m sub 0. Now, notice that the only assumption that we're making here, and on the previous slide, is that the population is continuous. There's no assumption of normality. There's not even an assumption that the population is symmetric. All right. So at this point, our development is not limited to situations where the distributions are symmetric or normal. Now, for each I going from 1 little n, we're going to, again, as we've done in the past, define this new indicator random variable, x sub I, which is 1 if y sub I is greater than the hypothesized value of the population median, cap m sub 0, and x sub I is equal to 0 otherwise. And then we're going to define this new random variable as the sum of the x sub i's. This new random variable is x tot. In words, x tot is just the number of the y sub i's, the number of the sample values that are strictly greater than the hypothesized value cap m sub 0. Now, continuing on with our development that we've looked at before, but again, just going through it again to be very careful to identify any assumptions that we're making. Note that the probability that y sub I is greater than cap m sub 0 is going to be the same for every observation in the sample because the sample values are identically distributed. In addition, since they're independent, each of these events, y sub I being greater than cap m sub 0, are independent as well. And so that means that the x sub i's that we're adding up to get x tot are independent. Finally, x tot is counting the number of what we might call successes, a success being y sub I being greater than cap m sub 0. X tot is counting the number of times that sample values are greater than cap m sub 0, the hypothesized value. And so because of all that, it turns out that x tot has a binomial distribution with n trials and success probability p. We see here in this development we've not introduced any additional assumptions. There are no additional assumptions that have been included here above and beyond the original assumption that the distribution or population that we're sampling from is continuous. So the next question that we had to consider in our development of this procedure was how do the possible values of p compare under the null and alternative hypotheses? Remember what we need to do. We need to understand the differences in how the test statistic behaves under the conditions of the null hypothesis and under the conditions of the alternative hypothesis. And in this case, the n here in this binomial distribution corresponds to the sample size, so that's not going to depend on either of the hypotheses. The only parameter here that's going to be affected is this success probability p, and so that is why we need to think about very carefully how p changes if the null hypothesis is true or if the alternative hypothesis is true. And so we need to think about the sampling distribution of the test statistic under those two hypotheses. Now, it was at this point in our original development that we utilized a graphic showing two symmetric, and in particular, normal distributions in order to help determine visually how that success probability p varies depending upon whether the null hypothesis or the alternative hypothesis is true. Now, that particular graphic and its explanation is again provided on the next slide so that we can remember what we were looking at. So this is where we introduced these symmetric curves, and in fact these are PDFs of normal distributions. And the reason we looked at this was to see how p changes depending upon whether the null hypothesis is true or the alternative hypothesis is true. And so again, this graphic shows two distributions, one with median equal to cap m sub 0, that's the green PDF here. And so cap m sub 0 is the median of that distribution, and so we know that the area under that green curve to the right of cap m sub 0 is 0.5. That is why we can say here that if the boundary condition of the null hypothesis is true, in other words, if the median of the distribution is in fact cap m sub 0, then P is equal to 0.5. That success probability in that binomial distribution, which is the sampling distribution of X tote, is 0.5. On the other hand, if the median CAPM is greater than CAPM sub 0, so if it's over here to the right somewhere, like right there, the distribution that we're sampling from would actually be this red curve. So if that's the median of the red curve, then we know that the probability under the red curve to the right of CAPM is 0.5. But there's additional area here under this red curve between CAPM sub 0 and CAPM. And so we know that the area under the red curve to the right of CAPM sub 0 is something bigger than 0.5. That is what we're saying here. If the alternative hypothesis is true, if CAPM, the true population median, is greater than the hypothesized value, then P, the success probability, the probability of an observation being greater than M sub 0, is greater than 0.5. And in fact, in general, the larger CAPM is, the greater the value of P. So this is where we introduced these symmetric curves, but the described effect on P that we just went through is not at all dependent on the underlying population being normal or even symmetric. But now that we're comfortable with this development, we can utilize a more general distribution in our development of the procedure so that we're not led into thinking that the distribution has to be symmetric. And so the next slide shows that same explanation of the effect on P using a highly skewed distribution. So let's take a look at this. So this is the same kind of argument that we had, but now we're not using symmetric distributions at all. You can see that both of these distributions are highly right skewed. So this graphic shows two highly right skewed distributions. The green one having a median equal to CAPM sub 0. And what that means is that the area under this curve to the left of CAPM sub 0 is 0.5. The area under the green curve to the right of CAPM sub 0 is also 0.5. We also have another right skewed distribution that has a median which we're labeling by CAPM, and that median is to the right of CAPM sub 0. So the red curve corresponds to this right skewed distribution, the median of which is located here at CAPM. So again, what that would mean for the red curve is that the area under the curve to the left of CAPM is 0.5, and the area under the red curve to the right of CAPM is also 0.5. Now, it may not quite look like that, but keep in mind that this distribution, this right tail, goes out to infinity. If we look at this graph, if the boundary condition of that null hypothesis is true, in other words, if the median of the distribution is CAPM sub 0, then the probability of getting a y value greater than CAPM sub 0 is given by the area under the green curve to the right of that point, and we said that was 0.5. On the other hand, if the alternative is true, so that the distribution has a median here at CAPM, then the probability of getting an observation, a value of y greater than CAPM sub 0, is going to be the area under the red curve to the right of CAPM sub 0. Well, we know that this area out here to the right of CAPM is 0.5, and this area under the red curve between CAPM sub 0 and CAPM is greater than 0, obviously, and so the area under the red curve to the right of CAPM sub 0 is certainly greater than 0.5. And again, the larger CAPM is, the greater the value of P. And so then we can continue on with this development just as we did when we first looked at it. If the boundary condition of the null hypothesis is true, then our potential or candidate test statistic X tote has a binomial distribution where P is equal to 0.5. On the other hand, if the alternative is true, if CAPM is greater than CAPM sub 0, then while X tote still has a binomial distribution, the success probability is greater than 0.5. And so these results imply that the mean of the distribution of X tote is n over 2 if the boundary condition of the null hypothesis is true, and if the alternative hypothesis is true, then the mean of the sampling distribution of X tote is greater than n over 2. Hence, if the alternative hypothesis is true, the random variable X tote will tend to be larger than it is when the null hypothesis is true. Therefore, large values of X tote provide evidence against the null hypothesis and in favor of the alternative hypothesis. So we've again identified this differential behavior of this random variable X tote under the null hypothesis and under the alternative hypothesis. And again, we ask, how do we come up with decision criteria for rejecting the null hypothesis? Well, so the next slide shows the sampling distribution of X tote when the boundary condition of the null hypothesis is true. it's the same as it was before. All right, this is an example where n is equal to 10. If the boundary condition of the null hypothesis is true, then p is equal to 0.5, and so the resulting binomial distribution, which is the sampling distribution of x tot, is perfectly symmetric. And so, again, we finish off the development in the same exact way that we did before. So there's really no need for us to continue on with this other than to say, we're trying to figure out how to come up with the rejection criteria for this right-tailed test and how to calculate the p-value. But these calculations, these determinations and these calculations are exactly the same as they were before. For example, we can express the p-value in terms of the PMF of the binomial distribution or in terms of the CDF. Okay, so having said all that, we see that the results of the development, right, the procedure that we ended up with remains exactly the same as it was before in our previous development. What assumptions did we make? We were trying to be careful to identify any assumptions that we made in the development of that process or that procedure. The only assumption we made was that the population that we're sampling from was continuous. It was the distribution of a continuous random variable. We have not assumed that the population is normally distributed. We have not assumed even that it's symmetric. In fact, we've shown that we can use a skewed distribution to come up with the appropriate rejection criteria for evaluating the test statistic. So since we have not assumed in this development that the population being sampled is normally or distributed or even symmetric, but only that it's a continuous population, the procedure is valid for any continuous distribution, regardless of its shape or the heaviness of its tails. Right, so that's so important for us to see. Even though we've used these examples and these demonstrations using a symmetric curve, there's nothing about this procedure or in its development that requires that the population that we apply this procedure to be symmetric. And that's a good thing, because if you think about it, there probably aren't too many distributions or populations out there that are perfectly symmetric. And so we can apply this procedure to any population that is a continuous population. Okay, so the next example is going to demonstrate this. We're going to apply the procedure to test a hypothesis about the median of a highly right-skewed, heavy-tailed distribution. Okay, so this is example 2.7. Okay, so the data in the table below are a random sample from a population that is known to be highly right-skewed and heavy-tailed. Now, just out of curiosity, can you look at those data, and by looking at them, can you tell that the data set itself, whether or not it is right-skewed? Probably not. I know I can't. I need to do additional analyses, maybe make some graphics. All right, so that shows the importance of actually doing that. Okay, but this data set comes from a distribution or a population that is known to be highly right-skewed and heavy-tailed. The median of the population is unknown. The question of interest is whether there is sufficient evidence at a 0.05 level of significance to conclude that the median of the population is greater than 10. So we can scan through here and see that some of the values are less than 10, some are greater than 10. The question is there enough evidence in the data at the 0.05 level of significance to conclude that the median of the population is greater than 10? Now, summary statistics for this sample are provided on the next slide, and you might want to calculate the summary statistics on your own using your calculator just to verify these values and to get practice calculating those summary statistics. So we see that we've got a sample size of 30, the sample mean is 15.293, the sample standard deviation is 12.2815. I've included the skewness, the sample skewness coefficient here. It's equal to 1.354. The sample median is 13.5. Now, remember, we're wanting to test the null hypothesis that the population median is no more than 10 against the alternative that the median is greater than 10. Well, we see the sample median is certainly greater than 10. Is there enough evidence in the data to convince us that the population median is greater than 10? Well, we'll have to find out. And then X tot, which is the number of observations in the original data set or in the sample that are strictly greater than 10, that value is 20. And I would encourage you to go back and just to verify that. Now, I've also included a histogram of the sample. I've calculated these summary statistics and constructed this histogram in SAS. At some point, I'm going to show you some SAS code, but not quite yet. Now, based on this histogram, we can see that the data set is right skewed. All right, so we said we sampled from a population that is known to be right skewed, and we see here that the sample is reflecting that skewness. So the sample is right skewed as well. Okay, so the null and alternative hypotheses are as follows. So the alternative is that cap M is greater than 10, and that is what we're trying to show, and so that goes in the alternative. The opposite of that goes in the null hypothesis. So our null hypothesis is that the population median is no more than 10. Now, if the boundary condition of the null hypothesis is true, specifically if the population median is equal to 10, then EXST, our test statistic, has a binomial distribution with n equal to the sample size, which is 30, and a success probability of 0.5. Now the next slide shows some information about the sampling distribution. And so we see here, this is the sampling distribution of EXST if the boundary condition of the null hypothesis is true. All right, so we see that it's a perfectly symmetric binomial distribution. And remember that we're looking for large values of EXST in order to reject the null hypothesis. All right, and so the question would be, what would be considered unusual if the null hypothesis were true? Well, if the null hypothesis were true, and in particular if we're looking for large values of EXST, then values out here in the right tail would be unusual because they have such small probability. So here I have kind of my standard slide here for getting information about the sampling distribution of EXST. So I've got the instructions for constructing the distribution, the sample space, and the CDF, and 1 minus the CDF. All right, and so what we're looking for, since we're looking for large values of EXST that are unusual, and we're also keeping in mind that we want the significance level of a test to be 0.05 or something close to 0.05 without going over. If we look in list L3 in the bottom right panel, if we look for a value that is the largest value that is less than or equal to 0.05, then we see 0.0494 here in the row corresponding to 19. Okay, now remember that this corresponds to a probability that EXST is greater than 19. And so in coming up with our rejection criteria, we would reject the null hypothesis if EXST is strictly greater than 19. And because of the discreteness of the sample space, EXST is greater than 19 if and only if it's greater than or equal to 20. And so we could specify the rejection criteria in either of these two ways. We could also express it in terms of the p-value, right? We could say that we're going to reject the null hypothesis if the p-value is less than or equal to 0.05, which in this case is equivalent to saying that we're going to reject if the p-value is less than or equal to 0.0494. Since that is the closest attainable significance level that is less than or equal to 0.05. All right, now we established before that EXST, the value of the test statistic, is 20, so the p-value is equal to the probability that EXST is greater than or equal to that observed value under the conditions of the null hypothesis, and that p-value then is 0.0494. And so since EXST is greater than or equal to 20, and equivalently, since the p-value is less than or equal to 0.0494, we can say that there is sufficient evidence at the 0.0494 level of significance to reject the null hypothesis and conclude that the median of the distribution is greater than 10. Okay, so that's the end of this example. Again, why did we go through this? Why did we go through another example? To demonstrate that we can apply this procedure to any continuous distribution, even a distribution that is highly right skewed and or has heavy tails. In fact, this distribution, I'll just tell you that this distribution that we got this data from is an exponential distribution. The exponential distribution, these are exponential distribution curves as well. And so the exponential distribution has a skewness coefficient of 2, which is quite different than the normal, right? The normal distribution has a skewness coefficient of 0 because it's symmetric, right? But the exponential distribution is highly right skewed. In fact, its skewness coefficient is 2. And not only that, the kurtosis of the exponential distribution is 3 times larger than the kurtosis coefficient for the normal distribution. So the tails of the exponential distribution is much, much heavier than the tail of the normal distribution. That kind of heaviness of tail is sometimes an even bigger problem when applying statistical procedures than skewness can be. We know that because of the central limit theorem, in many cases, skewness of the sampling distribution of a statistic is attenuated by increasing sample size. Problem associated with kurtosis can also be somewhat mitigated by large samples, but it's not mitigated as quickly. Again, the bottom line here, and the reason for looking at this, is to demonstrate and to help emphasize the fact that the procedure that we've looked at is very, very, very general. It does not depend on normality, it does not even depend on symmetry, it does not depend on the distribution having the same heaviness of tails as the normal distribution. The only assumption that we have used here in developing the procedure, the only assumption that we have made here is that the distribution is continuous, okay? So this procedure is applicable to any continuous population. Okay, that wraps up this video. We'll continue on and finish up this particular topic in the next video or two.